Hey there, so today we are going to be talking about describing graphs. So the first thing we're going to do is we're going to be looking at these graphs, and in particular we're going to be looking at how these graphs can be described in terms of rate of change. So I look at the first graph here. I have this nice little line right here, and I want to say, how does the rate of change can be compared, for instance, from the middle of the graph, to up here, to the beginning of the graph, anywhere. And what I would probably say to that is, it doesn't matter where I am on the line, is that for every interval I go in the horizontal direction and go up, it's kind of consistent. It keeps going up and up and up. So in other words, if I went 3 units this way, I would get 3 units this way, 4 units this way, I would have to go 4 units this way. It's always going to be the same. And when that happens, that's called a linear relationship. And we can see that because it forms a nice line. Compared to, for instance, this graph down here, where, for instance, if I went 1 unit in this direction, it goes up to here. But if I went over, 4 units in this direction, I would, go way up here. And this would be considered a nonlinear relationship. Now this one up here, while it is made up of lines, it's still not a linear relation. For instance, here, the rate of change as it goes along this line is not the same as this line or this line. This one slopes up into the right. This one doesn't change over as the horizontal. And this one goes down and to the right. So this, even though it's made up of lines, is not a linear relationship because the rate of change is not the same throughout the graph. This one is a combination. Even though I do have linear lines, and then I still have this curved line right here, it's still not linear throughout. And that's what's important in determining whether a graph is a linear relation or a nonlinear. So let's write that down. So a linear relationship is one where the rate of change is the same over time. And it forms a straight line. Whereas the nonlinear relation is the rate of change varies over time. So let's keep that in mind as we continue on through the lesson. Oh, and let's add that, it does not necessarily form a straight line. But keep in mind it could, but if they have different slopes, say, then they're going to have different rates of change. Okay, so let's look at these table of values here. And from the table of values, without graphing them, we're going to decide if these are linear and nonlinear. So looking at the first one here, what I'm going to do, I'm going to look at how the x variable changes with each line. And then I'm going to look at how the y changes. If this were a linear relationship, the y will change at the same rate every time the x changes at the same rate. So in this one here, the first one changes by 1 unit, but this one changes by 3 units. It actually decreases by 3. This one goes up by 1, and this one decreases only by 1. Right here, I know that this is not a linear relationship. If it were, this negative 1 would be a negative 3. So this one is non-linear. I don't have to go any further than that. Let's look at this one here. Now again, this one has the exact same number, so this increases by 1 and this one increases by 1. This one increases by 5 from negative 8 to negative 3. From negative 3 to 2, well, that also increases by 5, so this one is looking pretty good. Let's keep going. This one increases by 5. This one increases by 5. Now this one to this one is a bigger jump. This one is a jump of 3. Now based on what we've done before, because this is a jump of 3 and this one is a jump of 5 from the previous steps, I would expect from 12 to 17 should be 15, which it is. So this one is a linear relation. Now let's look at this one right here. Now this one right here, same thing. We got a 1 jump, a 1, a 1, a 1, and a 3. Same numbers as in the previous ones. Now this one, you might notice that goes down by 0.5. And likewise, all up to here. These are all actually negative 0.5. And then we get to here. Well, from 5.5 down to 3, that's a jump of minus 2.5. And we got to see, is that going to be enough or is it too much? So if from 1 to 2, it was a jump of 2.5, we kind of write it over here. We can say, well, what should 3, 4, and 5 have been? Well, if 2 was 5.5, 3 should have been 4. Sorry, 3 should have been 5. It's 5.5 minus 0.5 is that. 4 should have been 5.0. And 5 should have been 4.5. But that's not the case. So in other words, there should have been a jump of 1.5 units less. However, this one is a little bit more. So this one is also nonlinear. And the last one. So this one jumps a little different. This goes 1, 2, 3, 4, and this one is 5. This one goes up by 5. So here, for 1 unit of increase, this one increased by 5. This would mean that if we went up 2 units of increase on this side, I would expect that this would go up by 10. And it does because it goes from 10 to 15. Likewise for 3, I would expect a jump of 15 units of increase. Because this 1 unit from here to here resulted in a 5 jump, going from 1 to 3, which is a jump of 2, I would expect this 10 to go to 20. However, in this case, it only goes to 15. Because of that, this does not have a linear relationship because these always go up by 5 on this side, but these values don't. These values go up 1, 2, 3, 4, 5. So they increase at a different rate on this side. So this one is non-linear as well. Okay, so let's move on. So now we're going to look at the idea of continuous versus discrete data sets. Now, the way to describe continuous versus discrete, a discrete data set is one that can only be counted with integers or very specific numbers, certain numbers can only be used. Whereas a continuous data is when you have two real numbers and all the real numbers in between make sense. And you're probably wondering, what does that mean? Well, let's think of it this way. Remember in Harry Potter, we heard of platform 9 3/4. Well, that was kind of silly because we think of platforms where we board a train as being numbered 1, 2, 3, 4. And that's why the 9 3/4, it doesn't make sense. It's in between those counting numbers. So that kind of thing is funny because normally it would be a discrete data set because we're counting the platforms, but they've kind of made it into a little bit of a continuous where we have this number in between. So let's look at some examples here. For instance, temperature. If we are recording the temperature throughout the day and at the morning it was 0 degrees, but by noon it was 10 degrees, well, we know it didn't just go from 0 to 10 degrees Celsius just like that and skip all the values in between. It actually hit every single one of those little values as it made its way up to 10 degrees. That idea would be an idea of a continuous data set. Another example of a continuous data set would be watching a plant grow over time. We may record those points on a given day, so every day we go out and we measure our height, and it may have grown from one day to the next, but we know it didn't skip all those heights in between. So that would be an example of a continuous data set. If we were filling a container up with water over time, well, we could measure the volume at certain points in time, but that doesn't mean that we didn't, start off with having it at this height before it got to hit this height and it went like instantaneously. No, it had to hit all the heights in between. So that means the volume of water as it fills gradually in container would also be a continuous data set. Let's look at a couple more examples of this to kind of get the idea of the difference between discrete and continuous data. So let's look at these two graphs right here. So the first one is an example of the points that the Lakers get on any given day. So we have 5 days, and from our table of values, we see, the first day they got 110 points. The next day, LeBron had an injury, so, points went down, they stayed down. On the third day, Anthony Davis, he had an injury too, so those guys are both out. But then the fifth day, they both came back and the points went up. Now, it doesn't make sense to join this up with a line. If I join this up with a line like this, what this is meaning is that on the 1.5th day, I draw a little line like this and a line like this. They got about 95 points, and that doesn't make sense because these values are discrete. The numbers in between don't make sense. So that's what we mean by it's discrete data, and only certain numbers can be used. However, if we go back to our example of the height of the plant on any given day, sorry. Oh, look, I didn't put my days in. Well, this one is a little bit of a different scenario, like we mentioned before. We may measure the heights at a certain time every day, but in the meantime, that plant is growing. So if we drew these with a line joining them up, it would make sense because in between day 1 and day 2, it makes sense that it was kind of between this height and this height. That makes perfect sense. It can be between those heights. Likewise, from day 2 to day 3, we got a big jump. Maybe it had great sunlight that day. It got a little drop of water. Well, again, we can count those points in between because it actually hit those points as it went from this height to this height. So that's another way we can think of continuous data versus discrete data. Discrete data, we can't join them with a line. It's a fabulous J. But in a continuous data set, we can connect with a line. Okay, so that's continuous and discrete. Let's move on to another one that we use, and that's independent versus dependent variables. Now, in our Lakers example and our plant example, we had days on the x-axis and we also had another variable on the y-axis, and height was one of them. These days and heights, those are considered variables, meaning that we can assign any value to them. But the idea is that one of these depends on the other one, but not vice versa. What we are going to be calling the independent variable, it changes the dependent variable. So whatever happens to the independent variable, it changes the dependent, but not the other way around. The dependent variable has no effect on the independent variable. So let's look at a couple of examples to kind of get an idea of what this actually means. For instance, as a child grows over time, would you say that the day depends on the height of the child, or the height of the child depends on the day? Think about that. Well, I would say that the height of the child depends on the day. Therefore, the height would be the dependent variable, and the day would be the independent variable. Therefore, this situation doesn't happen. Let's look at our other example here of driving to Calgary. In driving to Calgary, would we say the distance depends on the time? In other words, the longer I drive, the further I get? Or does the time depend on the distance? So what makes more sense there? The time depends on the distance, or the distance depends on the time? Well, think about that one. Well, in this case, the time doesn't depend on the distance, because the longer I drive, the further I get. So the distance is the dependent variable, and the time is the independent variable. Let's think of another one, climbing Mount Everest. We probably heard in science that as we go higher into the atmosphere, the temperature drops. Well, and that's the case, the temperature depends on the height, or does the height depend on the temperature? Well, remember, the higher we go, the colder it gets. So the temperature depends on the height, not the other way around. So in that case, this would be the temperature would be our dependent variable, and the height would be the independent variable. So I hope that clears that up. Now in general, our independent variable we are going to put on our x-axis. And you're going to find one of the most common independent variables is time. Time waits for no one. In other words, it depends on nothing, but everything depends on time. So time is always going to be independent, which makes our y-axis the dependent variable. Okay, so let's move on. So the next thing we're going to look at is this example over here. So here we have a graph that represents the water level in a bathtub over time. So I want you to pause the video, take a moment, and answer the questions below. Why is it continuous? Is it linear or nonlinear? What is the independent variable? What is the dependent variable? Describe what is happening on segments BC and DE. How long did it take to fill the bathtub? Take 8 inches in depth. And I want you to write a sentence for the scenario for segment CD. So pause the video, take a moment, and let's get that done. So the first thing we want to talk about is why is this continuous? Well, does it make sense that the volume can hit all the little pieces in between, sorry, the volume, the depth. We're talking about depth here. So the depth will increase all the little points in between. So it might be 1 inch, 2 inch, but it could be 1.5 inches. It could be 1.7777 repeating inches. It's all okay. All of those things make sense. So in this case, this would be a continuous data set. Next, is it linear or nonlinear? Like I said before, while the pieces of each graph are linear as we look at them separately, as a whole, the rate of change is different at this point of the graph, say to this point of the graph, to this point of the graph. So in this case, while the pieces might be lines, it's still nonlinear. So now we have to state the dependent and independent variable. And just as I mentioned before, time waits for no man. So time is the independent variable. And the depth of the water depends on the time. So the depth is the independent variable or the dependent variable. The next question asks, what is happening at BC and DE? Let's change that color so we can highlight it more. Well, the water level isn't changing. If the water level isn't changing, it must mean I turned off the faucet. So, the water stopped running. However you want to state that. So then it says, how long did it take to fill the bathtub to 8 inches in depth? Well, we find 8 inches over here. We go over until we hit the graph. When we hit the graph, then we head down. So that means the time that it took to hit the graph, the time that it took to fill to 8 inches was 4 minutes. So the last part, write a scenario for segment CD. So what possibly could have happened that this little piece of the graph had to happen? Well, if this is filling a tub, the tub was filling up, but then at this point, the tub stopped filling up because the height didn't change. Well, was the water turned off? Well, you can say anything. You can say the phone rang and you had to take a call. You could say, if you're in the water at this point, you could have thought, you could have thought, oh, this water is too cold, I need more hot, or this water is too warm, I need more cold. Anything will do. But say the phone rang and you couldn't watch it. Anything is going to work for that. Like I said, some of these questions, there's always more than one right answer. So let's look at one last example. Okay, so it's Canada Day, and they are setting off fireworks. Specifically, every minute they set off 20 firework shells. The question is asking, assign a variable for the number of firework shells, assign a variable for the time elapsed in minutes, explain which variable is dependent and which is independent, create a table of values, and a graph for the relation. Is it linear, nonlinear, or is it discrete or continuous? Now I notice I left this from the last example. I'm going to erase that for you. So I want you to go ahead, pause the video, and when you're done, I want you to come back and take a peek. Okay, so the first thing I did, I said that my x was going to be the time. Now, if you wanted to say that instead of x, if you wanted to put t, that's perfectly well, t for time. Likewise, I said my y was the number of shells. And again, if you wanted to put y, that's fine. But, if you wanted to put f for firework shells, you could do that too. So we have the time and the number of shells. Now, again, time waits for no man. So time is the independent variable. So I'm going to put time on my x-axis, and it's going to be in minutes. You want to make sure that if you have a unit, you want to put it in so that your information is clear. Now this one is your number of shells. Now number of shells doesn't have a unit, so we're going to put that there. And then here we're going to put a title and number of shells versus time. Usually it's y versus x, whatever that is in your graph. And then we're going to create the table of values. So I picked easy numbers, 0, 1, 2, 3, 4, and every minute I added 20 to create my table of values. Now I'm going to plot them. 1, 40, and then 60, and 80, just like that. Now it's asking if it's linear or nonlinear. Well, because as this changes with a constant rate, it goes up by 1 every time, that this side also changes with a constant rate, this is going to be considered a linear graph. That makes sense. The next one, though, is a continuous graph. Well, it is a line, but lines don't always mean it's continuous because the values in between have to make sense. Well, in this one, nothing happens between 1 minute and 2 minutes. It says every minute 20 fireworks shells are set off. So nothing happens between here. So it doesn't make sense to join this line up from here to here, because these points in the middle don't make sense to this little story we're being told about fireworks. So in that case, this is continuous. Sorry, my bad. I see continuous, so I write continuous. Is discrete, because the points, the values in between don't make sense. No fireworks are being set off between the minutes. And that's the end of the question. If you have any questions about any of the examples we've done in this video, please do not hesitate to ask. I hope you have a lovely rest of your day. Take care.